And we can go to the advanced demonstrators, but I want to explain you in this example what they are about to give you an idea what eFMI can do. Let's look into the advanced examples. The first one is something that you can also see at our DS booth, where you can play yourself with it, where you have a little hardware setup. And that is a battery management system. So this battery management system is operating a passive cooled battery to meet the power request as good as possible without endangering the battery to overheating. Our controller we want to deploy is a real-time simulation of the battery cell plus the control code. And we use the real-time simulation of the battery cell to know what is the temperature of the battery, such that the controller can limit power request, because there is no physical temperature sensor available. So we need a virtual sensor to know what is really the cell temperature. That's why you want this battery model. This is done all in Modelica. So we have the battery cell model, which is a hard real-time simulation of the electric and terminal behavior of the battery. It's a prediction model, a virtual sensor, a virtual twin. These are the terms people use. And then in this model, we have the control logic. There's a controller, but that is very, very simple, because it essentially you get a power request, and this controller will limit the power request to ensure the safe operation. It's nothing more. So the power controller is simple. So the inputs we have is the power request. Then we have some tunable parameters, which are the ambient temperature, because it's a passive cooled system. It just takes the ambient temperature to conduct the heat. And why is it a tunable parameter? Because there are many scenarios where the ambient temperature is constant, like say an industry environment, so it's not changing anyway. And in other cases, it's not going to change super fast. You don't need it every 2 milliseconds or something. We do it once in a while to update it. And the outputs is, that's basically everything you want to know about a battery. But most importantly, it's the actual provided power. So this may be limited, but also the status of the battery, like what is my temperature, the cell temperature, the voltage, the current, and all these things. The catch is we don't develop this model from scratch. Instead, we use our commercial battery library. That is very, very interesting, because we have a commercial battery library from the sources. This battery library has never been developed to be used in an embedded environment whatsoever. We just use that thing and take one battery cell model from there. In our case, it's a stupid example. We take just a very small little battery from Panasonic. It's completely out of order. You would never run it in the parameter settings we have here, but this is just to demonstrate. Even, of course, in reality, you would need for your battery the model. And it will be, let's say, in a car, you don't have a single cell, you have a cell pack, and then you have a load distribution of these things. But here we just take a single cell. And if you open that model, we have the battery, we have the power source, which is also simulated, we have the little controller, and here we have for the ambient, the thermal conduction. The battery is also its thermal conduction for the cell. And if you look under the battery, it has a thermal model. So this is the ambient thermal model, and this is the battery thermal model. Then it has an electric model, and it could have an AG model, but we come to that. The electric model is electric circuit plus some tables for interpolation of things. It's electric chemical model. And the thermal model, that's just the modeling of the conductions of the battery itself, so to say, the cell. And the AG model is deactivated. It makes no sense for the real-time controller. If you want to incorporate AG once in a while, you do it via recalibration. A few parameters have been tracked and you measure them through, and then you update other parameters that model the AG. And then we want to deploy this, and now it becomes interesting, on an Arduino Uno Rev3. It has 32 kilobyte of flash memory. It has 2 kilobyte of RAM. And it runs with 60 megahertz. And this model takes about 50% of the available memory, program and data memory. And we do it a sampling of every 10 milliseconds. And in fact, the do step requires 2 milliseconds on the Arduino Uno. And to deploy it, we use this that I described before via eFMI to generate the Arduino Uno sketch, where we have this template comments denoting the in and outputs, and then we connect it, and the code for scheduling and testing, the scheduling and timing. And we use the Arduino IDE basically. And we have at the DS booth where you have the setup with Arduino Uno, and then you have two potentiometers. The one you can change your request on the battery, how much power you want. And the other one you can change the ambient temperature, so you can fastly play with it. We don't take the ambient temperature here. It wouldn't make a lot of sense. Nothing would change, most likely. And then you get the plots where you see what is requested, black, and what is delivered, the power. You see the thermal model, where you see how the temperature of the cell core, the simulated one, is changing. And you see the lower and upper limits. This is basically the lower limit is when it would start to reduce the request because it got too hot. It's like a hysteresis. The upper limit is the highest temperature we permit for the cell. It must not get over that. And at some point, if you request less power, it will cool down. And then like a hysteresis, when it gets below the green line, then it will deliver the power again that you wanted. And here you have the ambient temperature. And we can have a look into that example. This is a little video that Christopher Stromberger made, a colleague. So we have the Arduino board. This LED is showing you essentially how well do we meet the demand. If it's red, we very much reduce the power. If it's green, it's all fine. So at the beginning, of course, it's fine. And then Christopher will start to put a request in, where he requests some power. Then he will put in some meter. And then you see how the temperature is starting to go up. And then at some point, it's starting to limit because the battery got too hot. I mean, it's a crazy scenario. It's a very small battery cell. And we request like something like 25 watt would be out of order. So it gets super hot. Then we increase the ambient temperature, where you see, okay, no, wait. No, you see it's completely working out of scope. It's getting hotter and hotter because the ambient is so hot. Then it reduces a little bit the ambient temperature, and you see how it goes down again. And at some point, it's below the limit, so we slowly can meet the request again. Yeah, so this is the idea. It's a little bit, the big battery is an artificial example, but it's from stock model that everybody can understand. But otherwise, it's a nice demo, I think. The second example is something where we also have later presentation paper about. It's a neural quarter vehicle model. So it's a prediction model for the vertical dynamics of a quarter vehicle model, incorporating the unknown nonlinear behavior of the suspension, so that's a spring and a damper, via neural networks. First of all, we have later a paper presentation about it, and you can read a conference paper in the app. It's on Wednesday, 9:15, on the Control and AI session. It's an open source model. It's already part of eFMI test cases. We had a recent eFMI test cases release where this model is included. And you see here, these are the trained neural networks. And you see these funny interfaces here, the Modelica flow interfaces. That's cool because it means essentially if you remove these neural networks, you just get linear behavior or this linear spring and damper. And if you add this neural, activate them, they only add the additional nonlinear behavior. So they are additive to the linear behavior. We have two neural networks. The neural networks are modeled using the eFMI library, which is public available. And there's a new package called neural networks, where you can essentially model a Modelica neural networks. It's open source. This is only about modeling the neural network, not about training. Training you have to do somewhere else. You have to train somewhere, and then you get the weights and biases. Yeah, the neural network parameters, the weights and biases, they can be online recalibrated. So they can become an eFMI tunable parameters, and then you can tune at runtime. You don't want in such a small embedded device potentially do the training online. That's too expensive. But maybe you can upload from your thing that you have from time to time some parameters and stuff, and then somebody can offline retrain the nets, and at some point you recalibrate your controller, and then you get the new behavior. Interesting is that the next timer, the 2026X, it will preserve the multidimensional TensorFlow in the generated Gallic code. It doesn't scalarize. You get a proper TensorFlow in Gallic. Remember, we have multidimensional arithmetics. You get a TensorFlow that's like that. And then a production code generator can optimize that. So typical use cases for such a quarter vehicle model is if you have semi-active suspension control in the car, then you can control the damper, the active part. You can also use it for fault detection. That would be also a typical use case, like if something wrong with the wheel or with the suspension. How does this look like? This is our model. Now this thing here is modeled like this. It's a normal TensorFlow, and in this case has 4 layers, a scaling and descaling. And here you have the weights for the layers. Such a layer has an activation function, and it has an activation type. In this case, we only support dense networks, so everything is connected with everything, and it has an activation function. And this is actually coming from the eFMI, from the public library, where we have the dense layer. This is this here. And then they are also provided different activation functions. So Dumoulin can right click here, choose all matches, and then you just pick your function, very convenient. And you get the weights, you double click, and you can just edit the weight and bias matrix, which defines essentially how many inputs and outputs you have there. Input and output sizes of the multidimensional are automatically derived from the weight and bias matrices. So this is the way to handle all this variability, because at the end you can just drag and drop these different network layers and connect, and you're done. This is new in the recent release, 4th of September, in the new eFMI library release. And if you use this library to model a network like this, and you put it into your model that is subject for embedded code generation, then you have the option that you want to preserve the multi-dimensions. So you go to your eFMU configuration, you pick the code configuration, and there you say multi-dimensional arithmetics. You want to keep them. That's the new prototype. I want to emphasize it's really prototype. It's a work in progress, but for the neural networks, you can guarantee it will work. For general Modelica models, it's really prototypical stage on how this works, how the neural networks works. And then we can compare our old code generation with the new. If we have the scalarized code for this example, so this has 2 networks, each has 600 parameters. If you compare the scalarized case, it would be 117 kilobyte for the TensorFlow. And in the new case, when we preserve the multi-dimension, the Gallic code, we have 2.77 kilobyte. So here you really see you just have the weights times the input plus the bias. And then afterwards, the activation function, and this is ReLU, takes at least 0, and otherwise it's linear. And you see here, this huge part of code is only for the first dimension. And this is for the second. So we have this, in this case, 16 times. This is super linear going. And then, if you look at the Lusolage solution, what we see essentially is that the neural network code size is dominated by the weights and biases. And you can't get below the weights and biases. If you think about a Gallic, it's like 29.3 kilobyte Gallic code, just weights and biases. And the minimum you need, if you would have 32-bit floating point, so this is Gallic code, production code generator can achieve this here, this 4.8 kilobyte. But this is really the minimum you need, because that's basically floating point values. And it's 2 times 600 neural network parameters times 4 byte for representing a 32-bit floating point. That's why you get 4.8 kilobyte. Below that, you can't go. Interesting is this here, when we say this is still Gallic code, 2.77 kilobyte. Of course, if you look at the production code, it generates your C code with some for loops here to do the multidimensional operations. It is clever. It merges the loops together to reduce the number of loops of software production engineering. So we don't do naive looping around it. We don't loop for the multiplication and afterwards loop again to add the bias. No, we squeeze it into one loop, so to say. And of course, the instructions for binary instructions, I would expect this to be less than this, because this is very talkative. I cut here the names. In reality, these names are even longer. So this is just the source code. So it's quite fat. But this number here, you can't get below that. We compare this also with ONX2C code generator, and then our code is more compact. More about that in the presentation and for the paper. And by the way, the paper is written that this doesn't work yet. The scalarization is an open issue, but in the meantime, we fixed it, so can support it. In the paper, it's still a future challenge.